Today we discuss about Cauchy Schwarz theorem. Cauchy Schwarz theorem or Cauchy Schwarz inequality is better. Cauchy Schwarz inequality. Let V be a vector space, then we have mod of norm of xy less than equal to norm of x multiplied by norm of y for all xy belongs to V. The equality occurs if and only if one of them is scalar multiple of others. Now we prove this one. Simply we start with if x equal to 0 or y equal to 0, then this inner product of xy equal to 0. Okay, and either this case and either inner product of xx equal to 0 or inner product of yy equal to 0. Hence the result comes. Okay, then we now considered this one case 1. Okay, this one case 1 done. Now consider case 2. Then here we state that norm of x equal to 1 and norm of y equal to 1. If this one happened, then what we find? Then we considered x minus y inner product. Then this equal to is obviously greater than equal to 0. That means x minus y equal to xx minus xy minus yx plus yy. This equal to norm x minus xy 2xy plus norm y. This equal to 2 minus 2 xy inner product. Here norm x and norm y is 1. So we erase this portion and going to further step. Then here also we considered x plus y and x plus y inner product. That means in this case we consider x plus y this inner product. This inner product obviously greater than equal to 0. This implies that xx plus xy plus yx plus yy greater than equal to 0. This implies that 2 plus 2xy greater than equal to 0. This implies that minus xy less than equal to 1. Okay. So what we find? We find here minus xy less than equal to 1 and another one xy less than equal to 1. So mod of inner product of xy less than equal to 1 we find mod of inner product of xy less than equal to 1. Fine. And this one equal to what? This one equal to norm of x multiplied by norm of y. Okay, so we get the required result when norm of x equal to 1 and norm of y equal to 1. So we erase this portion now also. Now going further. Now we going further. The portion here. Let x y inner product mod equal to 1. Then either inner product of x y equal to 1 or inner product of x y equal to -1. Okay, if inner product of x y equal to 1, then what happened? Then we get x minus y equal to 0. This implies that x equal to y. And if inner product of x y equal to -1, then what happens? Then x plus y equal to 0 implies that x equal to -y. Okay, then the equality holds if and only if. Then the equality holds if and only if x equal to plus minus y. Again we construct when x y are non-zero and not necessarily of unit length. When we construct x y are not 0, now we construct suppose x y non-zero and not necessarily of unit length. Then what we do? Then we construct u equal to x y norm x and v equal to y norm y. Then simply u v are of unit length. Then in previous way we get, then by previous case we get inner product of u v mod of this less than equal to norm of u norm of v. This implies that inner product of x norm x y norm y mod less than equal to 1. This implies that inner product of x y less than equal to norm of x norm of y. Okay, I think all are understand this. Now I going further. That means if equality hold, then what we done? Where is this person? If equality hold, then what we done? If equality hold, that means if x y non-zero, then equality means that x y equal to norm x norm y. One chance and another one is minus x y equal to norm x norm y. Okay, assume first one happened, then assume first one happened, then xy equal to norm of x norm of y. This implies that y x y norm x y norm y equal to 1. Okay, this implies that x y norm x equal to y norm y. This implies y x equal to norm x y norm y into y. So this one is happened, and we considered other case. Other case means this one equal to this one, then here this one, here some and this one, and here some this one happen. So Cauchy Schwarz inequality is completely done today, and we apply Cauchy Schwarz inequality in any other portions. Now we discuss about the definition of norm. Previous class we also discuss about definition of inner product and see some example of inner product. Now we discuss about definition of norm. Too easy portion. We done it. Definition of norm. Norm, a V vector space, V vector space, and given a vector x, given a vector x belongs to V, we define the norm. We define the norm of x. Norm of or length of x. Norm or length of x. Norm or length of x. Norm or length, this one, norm of x as the non-negative square root, as the non-negative square root of inner product of this one. Okay, so we write it norm x equal to inner product of x. Now we define in Rn, we construct Rn, then x1 x2 xn are element x equal to x1 x2 dot xn, and y equal to y1 y2 dot yn. Then xy equal to summation I equal to 1 to n xi yi. Okay, and if r square, we consider r square. Then similarly norm of inner product of xy equal to xy norm. Okay, here norm of xy equal to this one, and here norm of xy equal to same thing, square root of x square y square. Inner product of these two is this one defined, and norm of this point is equal to this one. Okay, in this one, if we have any this balance, then this one equal to square root of xy norm, that means square root of x square plus y square. Okay, so we understand norm, and norm have certain properties. These properties are discussed now. The norm V2R has the following properties. First one, norm x greater than equal to 0 for all x belongs to V, and norm x equal to 0 if and only if x equal to 0. Number 2, number 2 norm have norm of alpha x equal to mod alpha norm x. Okay, alpha belongs to x belongs to V and alpha belongs to R. Mod satisfies those two properties, and if a unit vector x belongs to V, a unit vector x belongs to V, each of unit norm norm of x equal to 1. Okay, if this property satisfies. And also we discuss further property of norm. Now we going to one theorem, one important theorem on norm. Above this theorem we also see some example. Previous class we also discussed this example, but today we not handle this one. This example is if 0 to 1 to R be continuous, with ft equal to 0, with ft greater than equal to 0 for t belongs to 0 1, for t belongs to 0 1, then 0 1 if t dt equal to 0 if and only if t equal to 0 for all t belongs to 0 1. Okay, but if f is not continuous, but if f does not belongs to c01, then this conclusion is not hold. That means this 0 does not imply that ft equal to 0. We construct if t equal to 0 when t not equal to half and 1 when t equal to half, then f does not belongs to c01 and f 0 to 1 f dt equal to 0. So this portion is done. Okay, now we proceed further. Theorem of a norm. Theorem of a norm is an important topics to know the norm. So this topics we also discuss now. Theorem, we write this theorem first. The norm associated with an inner product on a vector space V satisfies the following. First one, norm x greater than equal to 0 for all x belongs to V, and norm x equal to 0 if and only if x equal to 0. Number 2, norm of alpha x equal to alpha norm of x for any scalar a and x belongs to V. And number 3, norm of x plus y less than equal to norm of x plus norm of y for all xy belongs to V. Now all proof of norm satisfies first two conditions are easy. Okay, norm of, we know about that this one is greater than equal to 0, so positive square root of this one greater than equal to 0, that means norm of x greater than equal to 0. If equal to 0, then this one x 0. If norm of x equal to 0, this implies by x equal to 0. And obviously norm of alpha x equal to square root of alpha x and alpha x. That means square root of alpha square xx. That means alpha xx. That means alpha norm of x. Where alpha belongs to R and x be also a inner product space where alpha is x belongs to R or C something. Here then we see that just triangle inequality, just beautiful triangle inequality. Okay, beautiful triangle inequality. We construct here x plus y square, then inner product of x y. Here xx plus xy plus yx plus yy. Okay, then this one equal to norm x plus norm y square, norm x square, norm y square plus 2 into norm x, norm y by Cauchy Schwarz inequality. We here used by Cauchy Schwarz inequality. Okay, this one less than equal to this one less than equal to this one, that means totally less than equal to this. Okay, you used here Cauchy Schwarz inequality, and this equal to norm x plus norm y square whole square. Okay, so for what we obtain norm of x plus y less than equal to norm x plus norm y. The norm satisfies these properties and this is hold now. So we done this small theorem. Now today is here stop, I think. If these three properties satisfies by any vector or any function, this function is norm on this vector space. Okay, we write it, then this one is stop. We write it now. If any that means let v be a vector space, let v be a vector space, let v be a vector space over R or C, a norm on V, a norm on V is a function, norm V to R satisfying the above three properties, satisfying the above three properties. Okay, and the pair V this function is called non-linear space, non-linear space. Okay, so today here stop.